We have to move now. The next speaker is Emmanuel Tsesmelis, that is connected by remote.
Yes, hello everyone.
Okay, very
Yes,
well.
I can share my screen if that's okay. I can.
Yes, perfect.
All right. Hopefully you can see the screen. Um, okay, I'll just go to full screen. Okay. Can you see that?
Yep, we can. Thank you.
Very good. Okay, thank you very much. So indeed, it's a pleasure to join this workshop today from a distance. Unfortunately, other things have kept me here in Geneva at CERN, but I'm very happy to be able to give a short presentation on CERN, emphasizing, of course, it's as an example of a large-scale research infrastructure in Europe, and of course, organizations could model on CERN to develop new research hubs and research infrastructure, and that is the purpose of this presentation. And of course, there are several colleagues of mine from CERN in the audience in person in Thessaloniki, which of course you can discuss with later. So CERN has indeed become the world's biggest laboratory of particle physics. We were founded 70 years ago, as has been mentioned earlier. And indeed, in those 70 years, we have developed a research infrastructure based on unique accelerator facilities. The latest one is, of course, the LHC, which you see here, which is a 27-kilometer perimeter synchrotron at the highest energies, working at 7 tera electron volts or very close to that. We are very special in the sense that we do, because of the size of this infrastructure, we do straddle the border between two host states, France and Switzerland, as you can see here. And the beginnings of the organization, although they did start in Switzerland, have very quickly moved into French territory because of the extent of the particle accelerators themselves. The main goal is, of course, fundamental science. It's a laboratory for particle physics and discovery science at the basic level, and that is quite distinguishes it perhaps from many other laboratories around the world. However, having said that, although the fundamental research is at the core of what we do here at CERN, in order to do that experimental particle physics, we do need the technology and the innovation, which some of it, as we have seen in the previous presentation, finds its way into society. But we actually operate at the frontier of technology and innovation. We are also very strong in training the next generation of scientists and engineers and technicians to be able to deliver and operate the unique equipment we have here at CERN. And of course, as we'll see later, most of these young early career students and researchers actually move into other fields beyond particle physics. Very importantly, this all happens within the context of an international collaboration. We are an international intergovernmental organization, and we depend very much on the contributions from many countries, as we'll see down the road. So looking at the fundamental research, I'll spend a minute on the core part of our mission, based around the particle physics research and discovery. And the two main directions of what we do. One is trying to understand the fundamental building blocks of matter, the elementary particles making up the universe around us, from the world we live in, the macroscopic world that we live in, all the way up to the quarks and the electrons down at very minute distances. A second direction of research is reproducing the very early conditions of the universe, a fraction of a second after the Big Bang itself, which occurred about 13.8 billion years ago. And this we do by reproducing the energy of the universe and temperature of the universe and the energy density as existed at that time in the particle colliders like the LHC. And we are very unique in that respect because at the moment, no one else can reproduce those conditions as we can at the high energy frontier of our collisions at the LHC. And of course, to get the full picture of the development of the universe from the very beginning until where we are today, there is a synergistic collaboration with astronomy and cosmology and astrophysics in order to produce the film of the history of the universe. So we help to answer these questions through experiments predominantly. There is a theoretical physics department here as well at CERN, but we are predominantly a experimental particle physics laboratory where many of our distinguished scientists and engineers have been recognized with Nobel Prizes in physics for the discoveries in the experimental particle physics here, Professor Carlo Rubbia, Simon van der Meer for his engineering insights and contributions to particle accelerators, and Georges Charpak for his contributions to particle detectors, all of which are very key elements in developing a unique and forefront particle physics program. Most recently, with the discovery of the Higgs boson here at CERN in 2012, the two of the theoretical physics proponents of that theory, dating back to the 1960s, were awarded the Nobel Prize in Physics in 2013, although the discovery and observation of the Higgs boson was made at the LHC by the ATLAS and CMS experiments. So what we need to do is to develop unique equipment in three key areas, namely in the particle accelerators, in the particle detectors, and thirdly, in the high performance computing to handle the big data volumes which come out of this of the LHC. And if you look at each one of these in turn, the laboratory has developed the LHC over about 25 years of R&D, which were required to develop the magnet systems in particular, to steer the beams in the circular trajectory around the beam, around the ring of the synchrotron, 100 meters underground, developing these unique magnets, both dipoles and also quadrupoles, to steer and to focus the particle beams at the collision points. So this is a synchrotron at the large scale end, and of course the development of what we heard earlier by the earlier speaker to other applications of that same technology is a very nice step of transfer of knowledge and technology to outside particle physics. We have, obviously, we need the particle detectors themselves to be able to record what happens in the LHC, and these are built up by collaborations, each of which consisting of thousands of engineers and physicists from around the world. Very close to 900 different universities participate in this program. And these detectors, the ATLAS and CMS detectors and the ATLAS and LHCb detectors, which are the four foundation experiments at the LHC, supplemented most recently by five smaller experiments around those interaction points. So you can imagine the particle beams circulating clockwise and anti-clockwise in the synchrotron and coming into collision at these four locations where these very large devices have been installed to record what comes out. And these are some of the collisions in these particle detectors. The challenge is, of course, to be able to record at such high rates of about more than 1 billion particle collisions per second, which have to be sorted out and filtered so that we only write out about 1 kilohertz. So that is a challenge in itself, working in a high rate, high radiation environment to be able to do this unique physics where these detectors measure the various characteristics of the particles that come out of the collision point. And this collision point is where the simulation, as it were, happens of the beginning of the universe. So the third part is the worldwide LHC computing grid. This is a very distributed computing resources pulling together CPU, cores from 170 data centers in more than 40 countries, starting off from where the data is produced at the experiments here at CERN in Geneva, and connecting up about more than 1.5 million processing cores, which act in unison as one big computer center, where the physicists store and process and analyze the data coming out of the LHC. Up to now, we've had about 1.5 exabytes of data, which has been produced at the LHC, which is a very large volume in any measure of these data production. We do have a very diverse scientific program beyond the LHC. I think it's worth pointing out that Isolde is one of our lower energy machines, but it has a component to it which is interesting to radioisotope production called MEDICIS. We have a unique facility in the world, the antiproton accelerator, which was mentioned earlier, and ELENA is part of that facility, which can be used for other purposes as well. And also a very unique, first of its kind experiment studying climate change and climate science at a particle accelerator, between the link of cosmic rays and the formation of clouds in the atmosphere. So a very diverse scientific program that complements the flagship LHC activity. So we have come a long way. CERN has played a very important role in the 70 years since it was founded in 1954. But there's a long way to go to understanding what is out there, and that will require certainly more input from theoretical physics, but also building a research infrastructure that will enable us to probe the structure of matter further, to probe the beginnings of the universe further, so we have a fuller understanding, particularly of the dark sector of the universe, which accounts for more than 95% of what we know is out there when we look up in the sky. So the first step in doing that is, of course, upgrading the LHC. This is a project which is in progress now. It is going to be installed during the years 2026 and to 2030, and it will develop or deliver 10 times more collisions than what currently is available in the LHC. And this will enable us to access rare phenomena, greater precision measurements, and also a greater discovery potential during its operation from the year 2030 until the beginning of the 2040s, which will see the completion of the LHC and its upgrade program. We are also in the process of looking what's beyond the LHC and its high luminosity upgrade. And one of the key features of this exercise is what has come out of the update of the so-called European Strategy for Particle Physics, which is the roadmap, the cornerstone of the roadmap for particle physics in Europe. And very high on that list was the development of a feasibility study, technical and financial feasibility study of a future circular collider report that will be actually now beginning of 2025. And this is a new research infrastructure based on 100 or between a 90 and 100 kilometer new ring, a new synchrotron operating initially as an electron-positron collider and subsequently as a hadron-hadron and ion-ion collider. Very similar to what we had between LEP and the LHC at CERN in the 90s and now. So this is still under discussion. We hope that it is approved by the end of this decade so that construction of that new research infrastructure can start in the early 2030s. So international collaboration, we were founded 70 years ago under the motto of Science for Peace by 12 European member states at the time. We have since the end of August of this year actually doubled the number of member states with the accession of Estonia as a member state. But it has progressively been increasing over the years, not only in number, but also in reach. You will see here countries which are not countries of Europe, which have joined either as a member state or as an associate member state. And these are countries which are beyond the European borders, but contribute to as an institutional partner of the organization. And we also have observer states and international organizations. You'll see here a number of countries which do not have institutional participation at CERN and in the governance of CERN, but we do have international cooperation agreements with about 50 non-member states and territories. It is quite a large organization. We have about 3,500 staff and graduates on our payroll, and we have, very importantly, close to 14,000 associates coming from visiting CERN to carry out their research from various universities around the world. And we have an annual operating budget of about 1.2 billion euro or million Swiss francs. This is where all the people come from, working with us, about 110 different nationalities coming from the countries which are listed there. And the numbers, of course, many of them come from member states, but as you can see, we have a sizable contribution of researchers and engineers from the associate and the non-member states as well, of the country of origin of where their home institutes are located. CERN is indeed a model for open and inclusive collaboration. The experiments themselves show that. Putting together a governance structure to govern the individual LET experiments is a task in itself, but they are models of consensus building, competition, and cooperation. I'm very happy to say that CERN is also behind the governance structure of Sesame, which is the synchrotron light source in Jordan, which is modeled on CERN's governance structure. And here you can see the members of Sesame from the wider Middle East region, which participate in the governance and the running of the organization. We are, in fact, engaging very much on the international scene as well, on platforms that value the science and help to shape the global agenda conducive to fact-based decision-making with empowered citizens. 2 points here. One is, of course, CERN is an observer with the United Nations General Assembly in New York, and that's our seat at the General Assembly. And also, we actively promote 7 of the Sustainable Development Goals with partners in the international system. And those are some of the examples which I show on where we contribute to the United Nations Sustainable Development Goals. And you notice here that Sesame features there very prominently, and also, I guess, innovation, energy, gender, education, and also health, which is particularly relevant to this workshop. So moving to technology innovation, indeed, CERN, there are many technological innovations which have found application from the laboratory of particle physics to the society. The World Wide Web was invented here at CERN to solve a particular problem of communication between the scientists in the late 1980s. And many of the applications today are in the area of medicine and healthcare, which is particularly relevant to this workshop, starting from the particle accelerators and their application to radiotherapy and particle therapy, medical imaging and diagnostics. PET scanners were pioneered here in Geneva in the 1970s, and CERN played a very important role in the initial development and continued to do so in bringing in latest developments in electronics and sensors to the next generation of PET scanners. A pixel detector making a 3D color X-ray image is a very unique application of pixel detectors of Atlas and CMS into medicine. As you can see here, a very beautiful photo of the human wrist. And also at Medicis, as I mentioned earlier, the production of innovative radioisotopes for research in nuclear medicine. There are other applications in aerospace, in industry, for autonomous driving, radiation monitoring in the ISS, and also cultural heritage measuring art. So these are applications beyond particle physics, whether it's in medicine or whether it's in other areas which I show here. CERN is very keen to transfer this knowledge and technology through a technology transfer office that we have implemented here at CERN, particularly of interest to the member states of the organization. And I'll finish off by saying a few words of education and training. We are very unique in the sense that we have a sizable community of young people that work with us. This is the age distribution of scientists working at CERN, where the peak is in the mid-20s. And these are typically PhD students which carry out their research at CERN at one of our facilities. The fact that this drops with age, in a way, it's very positive, because that shows that many of them move into other areas of first employment. About 50% go into industry, and about 20% into other fields, including government organizations, and only about a third continue in academia and research, about 10 to 15% in particle physics. So this is a very healthy, I would say, distribution of the students when they graduate and leave CERN and look for first employment, that their training at CERN actually makes them very attractive to potential employers beyond particle physics. We actually run several programs in education, training, and outreach. I mentioned the 3,000 PhD students that do the research with us from about several hundred universities from around the world. We have undergraduate summer student programs, bringing to CERN more than 300 summer students. And we have teacher programs, which are particularly interesting to train high school teachers from various countries around the world. And these teachers then go back to their home schools and convey the excitement of physics and science and STEM in general to their classrooms. So this is our new flagship education and training session, Science Gateway. It's the outreach center for the public, but it was inaugurated 1 year ago, essentially, in 2023. And from the 150,000 or so visitors that we had to the organization before COVID, with the opening of this Science Gateway facility, we are approaching 400,000 now in 1 year. So this is a wonderful example of where particle physics interfaces with the public for ages 5+. And it's truly a remarkable facility for that purpose. And this is where I finish. Of course, going back to the fundamental, the course subject of CERN is indeed to do fundamental physics. That is enshrined in our convention. But as you saw, that there are many other aspects to the organization, and its complexity is actually quite interesting in terms of technology and innovation, education and training, scientific diplomacy, and international collaboration. And I think we've managed to survive 70 years, and we will continue to play a crucial role in the journey of exploration. And some of that hopefully will find its way to society in the various channels which I referred to in my presentation. So thank you very much for your attention.
Instead of having fundamental research as the main topic, we have cancer research to come closer to the society. So we hope that we have CERN helping us to follow the example, and we keep the collaboration open. Thank you.
Thank you very much.
Thank you again.